voltage drop calculations are essential in electrical engineering to ensure that the voltage at the end of a circuit is within acceptable limits. Two common methods for calculating voltage drop are method 1, voltage drop equals 2 times K times L times I divided by circular mils, and method 2, voltage drop equals the square root of I times R times cosine theta plus X sine theta. Let's examine these methods and their implications. Method 1, voltage drop equals 2 times K times L times I divided by circular mils, where K is a constant based on conductor property and temperature in the cable, L is the length one way, I is the current, and cm is the cross-sectional area in circular mils. The concern with method 1 is that it does not consider power factor. Power factor is the ratio of real power to apparent power in an alternating current circuit. It represents the efficiency with which electrical power is used. Ignoring power factor can lead to significant errors in voltage drop calculations, especially in circuits with inductive loads like motors or transformers. Method 2, voltage drop equals the square root of I times R times cosine theta plus X sine theta, where theta is the power factor, R is the resistance of the cable, and X is the reactance of the cable. The advantage of method 2 is that it considers power factor. This provides more accurate voltage drop calculations, particularly in circuits where the power factor is significantly less than 1. Comparing calculations using method 1 against voltage drop tables often reveals significant differences. This discrepancy suggests that the voltage drop tables may have been derived using method 2, which considers power factor. Accurate voltage drop selection is paramount for several reasons. Firstly, incorrect wire sizing based on inaccurate voltage drop calculations can lead to overheating and premature failure of wires. Excessive voltage drop causes the conductor to dissipate more heat due to increased current flow, potentially exceeding its temperature rating and insulation capacity. Secondly, reduced equipment performance and efficiency can occur. Many electrical devices, such as motors and electronic equipment, are designed to operate within a specific voltage range. If the voltage drops too low due to excessive voltage drop, these devices may not function properly, leading to reduced performance and efficiency. Thirdly, safety hazards may arise. Excessive voltage drop can cause lights to dim, motors to stall, and electronic equipment to malfunction, potentially creating safety hazards for personnel and equipment. It's generally agreed that method 2, which considers power factor, is the more accurate and appropriate method for voltage drop calculations. It provides a more realistic estimate of the voltage drop in the circuit, ensuring proper wire sizing and avoiding potential safety and performance issues. When performing voltage drop calculations, it is recommended to use method 2. This method considers power factor and provides more accurate results. This approach helps ensure that the correct wire size is selected to meet the load requirements and maintain safe and efficient operation. To elaborate further, let's delve into the specifics of each variable in the voltage drop equations. Starting with method 1, the constant K represents the direct current resistance for 1 circular millifoot at a specific operating temperature. This value is typically provided in engineering handbooks or electrical codes, such as the National Electrical Code or NEC. The length L is the one-way length of the circuit in feet. It is crucial to use the one-way distance to accurately represent the total conductor length through which the current flows. The current I is the load current in amps flowing through the circuit. This value can be determined by the load's power consumption and voltage rating. The circular mils, abbreviated as cm, is the cross-sectional area of the conductor. It is a unit of area commonly used for wires and cables, and it is directly related to the conductor's ampacity. Now, let's examine the variables in method 2. The current I is the same as in method 1, representing the load current in amps. The resistance R is the alternating current resistance of the conductor per unit length, typically expressed in ohms per foot. This value accounts for the conductor's material properties and the effect of alternating current on the conductor's resistance. The reactance X is the inductive reactance of the conductor per unit length, also typically expressed in ohms per foot. Inductive reactance arises from the magnetic field produced by the alternating current flowing through the conductor. Cosine theta, or cos theta, represents the power factor of the load. As mentioned earlier, power factor is the ratio of real power to apparent power and indicates the efficiency with which electrical power is used. Sine theta, or sin theta, is the sine of the phase angle between voltage and current. It is related to the reactive power in the circuit. When applying these methods, it's essential to consider the specific characteristics of the circuit and load. For example, in circuits with long conductor lengths or high current loads, voltage drop can be more significant. Similarly, in circuits with low power factor loads, the impact of power factor on voltage drop becomes more pronounced. Furthermore, it's crucial to comply with applicable electrical codes and standards such as the NEC, which provide guidelines and requirements for voltage drop calculations and wire sizing. These codes often specify maximum allowable voltage drop limits to ensure safe and efficient operation of electrical systems. In summary, while both methods can be used to estimate voltage drop, Method 2, which considers power factor, offers greater accuracy and reliability, particularly in circuits with nonlinear loads or significant inductive reactance. Utilizing Method 2 and adhering to relevant codes and standards will help ensure proper wire sizing and minimize the risk of voltage-related issues in electrical systems. To provide further clarity, consider a scenario where 100 amp load is supplied by a 200-foot long circuit. Using Method 1 and neglecting power factor, the calculated voltage drop might be significantly lower than the actual voltage drop, especially if the load has a low power factor. This could lead to selecting a smaller wire size than necessary, resulting in overheating and reduced equipment performance. On the other hand, using Method 2 and considering the power factor, the calculated voltage drop will be more accurate, leading to a more appropriate wire size selection and minimizing the risk of voltage-related problems. To illustrate the importance of accurate wire sizing, let's discuss the potential consequences of undersized conductors. Firstly, as previously mentioned, undersized conductors can overheat due to excessive current flow. This can damage the insulation of the wires, potentially leading to short circuits and fires. Secondly, undersized conductors can cause equipment malfunction. Many electrical devices, such as motors, require a minimum voltage level to operate properly. If the voltage drops too low due to undersized conductors, the equipment may not function as intended or may even fail to operate altogether. Thirdly, undersized conductors can waste energy. When current flows through a conductor, some energy is lost as heat due to the conductor's resistance. If the conductor is undersized, its resistance will be higher, resulting in greater energy losses. In addition to the potential consequences of undersized conductors, it's also important to consider the impact of oversized conductors. While oversized conductors can provide lower voltage drop and reduced energy losses, they can also be more expensive and difficult to install. Therefore, it's essential to strike a balance between voltage drop, cost, and ease of installation when selecting the appropriate wire size. To further enhance your understanding of voltage drop calculations, I recommend consulting relevant electrical codes and standards, such as the NEC. These codes provide detailed guidelines and requirements for voltage drop calculations, wire sizing, and other electrical design considerations. Additionally, there are numerous resources available online and in print, including engineering handbooks, textbooks, and software tools that can assist you in performing voltage drop calculations and selecting the appropriate wire size for your application. Remember that accurate voltage drop calculations and proper wire sizing are crucial for ensuring the safe and efficient operation of electrical systems. By considering power factor, adhering to relevant codes and standards, and utilizing available resources, you can minimize the risk of voltage-related problems and ensure the reliability of your electrical installations. As a final note, it's important to emphasize that voltage drop calculations are just one aspect of electrical design. Other factors to consider include ampacity, short-circuit current rating, and environmental conditions. A comprehensive approach to electrical design will ensure that all of these factors are properly addressed, resulting in a safe and reliable electrical system. Remember to consult with a qualified electrical engineer or electrician if you have any questions or concerns about voltage drop calculations or other electrical design issues. They can provide valuable guidance and expertise to ensure that your electrical installations meet all applicable codes and standards. Furthermore, continuing education and professional development are essential for staying up to date with the latest advancements in electrical engineering and technology. Attending seminars, workshops, and conferences, as well as reading industry publications, will help you expand your knowledge and skills and improve your ability to design and maintain safe and efficient electrical systems.